Hi students, see, so far we have discussed all the chapters like part 1 and part 2. Both part 1 and part 2 have physical chemistry, inorganic chemistry and the organic chemistry. Today I am going to solve some question paper because you are very close to the examination. So I am going to solve some previous year examination question paper. See, first the chapter wise. In this video, you are going to learn some that solid state chemistry. The solid state, you have to concentrate more in that imperfections of solids, then density based numericals and that compound identification, then packing efficiency, calculation of the packing efficiency. So these things you have to more concentrate. So in in previous year question paper, all these things are repeatedly comes. Hi students, see, today we are going to discuss about the CBSE previous year question papers and the answer keys. We will discuss the chapter wise. Totally we have 16 chapters, but in this academic year, that is 2021 academic year, you have only 13 lessons. First lesson is the solid state. In this lesson, you have to concentrate these things, more concentrate these things. That means the number of atoms in a unit cell. Then the compound, the formula identifications. Then the packing efficiency calculation, density based numericals, the imperfections in solids, that is defects in solids. Then the last one, the electrical and the magnetic properties, not included in this academic year, that is academic year 2021 only. So this you don't want to study this electrical and the magnetic properties. The rest of these things mostly in previous year question papers, you can see, check the number of atoms in a unit cell, then formula identification. Usually this is based on the number of atoms in a unit cell, that is the formula identification. Then packing efficiency calculation, density based numericals. Every year you can see that without the density based numericals, that not question paper is not usually in that question paper. So this is very important one. Then the imperfections in solids, that is also very important. That's Frankel defects, Schottky defects, the different types of the defect, that is stoichiometric, non-stoichiometric defects. So these defects are main questions are come this part. So now here first we will see the identifications of the formula, that is formula usually used in this chapter, that is the contribution of the particle, a corner of a unit cell, usually 1/8. Then contribution of a particle for the face of a unit cell is 1/2, that is half. Then within the body of a unit cell, that is 1, and the edge length of the unit cell is 1/4. So these things you have to remember that are coming to memory. Then the ratio of the number of particles A and B present per unit cell gives the formula of the compound formed between the A and B. Now we will see the types of questions and the answers. Now look at this problem. A compound formed by elements A and B has a cubic structure in which A atoms are at the corners of the cube and B atoms are at the face center. That is FCC means face center cubic. Derive the formula of the compound. So first you must look at here the atoms, compound formed by elements of A cubic structure in which A atoms are at the corner. So you know that the contribution of the particles at corner usually the 1/8. Then the number of corner in a cubic 8. So here 1/8 into 8 it will become 1. That is A atoms of the corner of cube. Then this is A atoms. So A is equal to 1. Then look at the B. B atoms, here the B atoms are at the face centered cubic. Usually, the contribution of the particle on the face centered is 1 by 2, and in a cube, you have 6 faces. So, the number of atoms in here in face center, that is 3. So, here the ratio of the compound A is to B. So, here 1 is to 3. So, that the formula of the compound A and B3. So, this is the formula of the compound. AB3 is the formula of the compound. Now, we will see the next 2 different types of problems. See, the next numerical, an ionic compound made up of atoms A and B has FCC arrangement, that is face-centered cubic arrangement, in which atoms A are at the corners and atoms B are at the face centers. So, if one of the atom is missing from the corner, what is the simplest formula of compound? Here you must note down, if one of the atom is missing from the corner, this is the main point. So, here the contribution of atom, already you know that there is 1 by 8, that is in the corner. But here one of the atom is missing. That means 8 missing of atom 1. So, that 7. So, 7 into 1 by 8. So, atoms A, the contribution towards the atoms A unit cell is 7 into 1 by 8, because one of the atom is missing from the corner. That is why 7. So, 7 into 1 by 8, it will become 7 by 8. Next, look at this. And atoms B are the face center. So, atom B, so A is what? 7 by 8. B, you know that in face center cubic, that half of the arrangement, so that's 6 faces. So, it will become what? B is equal to 3. Now, the ratio of the compound is A is to B. That means 7 by 8 is to 3. So, it will become what? So, 8 3s are 24. So, A 7, B 24, or you can write it, E 7 is to 24, A is 7 and the B is 24. This is the formula of the compound. So, you must carefully read that question. If one of the atom is missing from the corner, that is why here I took the 7, because one atom. In the corner usually 8, one of atom is missing, so that 8. So, sharing of that atoms, that corner is 1 by 8, so that 7 into 1 by 8, it will become 7 by 8. So, look at this numerical. What is the formula of compound in which the element P forms CCP lattice, that is cubic close packing lattice, and atoms of Q occupy 2 by 3rd of tetrahedral voids. You must know that the number of voids usually depends the 2 types. One is the tetrahedral voids. Tetrahedral voids, that is closed sphere, in a closed sphere, and another one is octahedral voids. 2 types of voids are there. One is the tetrahedral void and the octahedral void. Here, usually the number of tetrahedral voids generated in the sphere usually 2n. Then, the number of octahedral voids generated in the sphere is n. This 1n. So, here the question is what? Number of the tetrahedral voids is generated. So that it will become 2. So, that means 2n. The octahedral voids is n. You have to remember, that means T. In a simple trick you have to use. T means 2. In alphabetical order, 2 for 2. O, 1. So, in octahedral voids is given here, you have to use the octahedral voids, and the number of void is generated 1n, and tetrahedral means 2n. Now, we'll solve this problem. So, what is the formula of the compound? The elements P form CCP. So, in the lattice, CC pilatus and the atoms of Q. So here usually the cube having there is 8 corner, so sharing of that contribution of that unit cell is 1 by 8. So here P is equal to 1, and the atoms of Q occupy 2 by 3. So P is what here 1, and the atoms of Q occupies 2 by 3rd of the tetrahedral voids. So you have to use the 2 by 3rd. The tetrahedral voids is what? 2. So that multiply into 2. So what is the Q value here? 4 by 3. Now the ratio of the compound. You have to identify the ratio of the compound. So ratio of the compound P is to Q. So that here P is what? 1 and the Q is 4 by 3. So the formula of the compound is P3Q4. So this is the formula of the compound of this element. That means the tetrahedral voids Q occupied 2 by 3rd of the tetrahedral voids, means the formula is P3Q4. In case of, suppose if this is the answer, in case here octahedral voids means you have to use N. I will write here. In case of the tetrahedral, that means octahedral. So octahedral voids means here octahedral voids, number of octahedral voids generated is 1n. So that here 1. That means 2 by 3rd of the octahedral void, so that into 1. So it will become 2 by 3. So 2 by 3 means the ratio of the PQ is 1 is to 2 by 3. So P3 and Q2. So this is the formula identification. Next the sum is density based numerical. The compound CuCl, the CuCl has copper 1 chloride has FCC structure, that is face centered cubic structure like zinc sulfide. So its density is 3.4 gram per centimeter cube. What is the length of the edge of the unit cell? Here the formula is, the density formula is D is equal to, or sometime using rho or D. D is equal to Z into M divided by A cube into Na. Here I will tell you the expression one by one. The D is indicates density. Then Z is number of atoms per unit cell. Here the FCC. Here the structure is what? FCC. Then M is indicates molar mass. Then our formula mass. Then A cube is a edge length and Na is a Avogadro number. Now just write it Z. What is Z here? We want to find out the edge length. Here the edge length is what? A cube. So Z is given. That means the compound of CuCl has FCC structure. So a number of atoms present in the FCC unit cell 4. So Z is equal to 4. Then next is what? M. The molar mass or formula mass is given for the copper 1 chloride. Here 99 gram per mole. So 99 gram per mole or mole inverse. Then Na is already given here, or you have to commit to memory this Na value, Avogadro, or sometime using N0, whatever it is, just write it here 6.022 into 10 power 23 mole inverse. So this is the Na value and the A cube. So we want to find out the A cube. That means A. We want to find out the A. Now apply this value into this formula and you will get the A value. So here the D is what here? Sorry, I missed the D. D is density. Density is 3.4 gram. So D is 3.4 gram per centimeter cube. So these things are given here. So I repeat here. Z is a unit cell, that is number of atoms per unit cell, that is 4. M is molar mass of the copper 1 chloride, that is 99 gram per mole. Then Na is Avogadro value, Avogadro constant, that is 6.022 into 10 power 23 mole inverse, and the D is 3.4 gram per centimeter cube. So we want to find out the A cube here. So that's mean rearrange this formula. The rearrangements of formula means what here? So A cube. So we want to find out the A cube. So rearrangements of the formula means that is Z into M, that is into D. D is here, the D will comes here and the Avogadro number. So Z into M divided by the D into Na. Now apply this value in this formula. So Z is what here? 4 and M is 99. Then D, density is 3.4 into Na is what? 6.022 into 10 power 23. Now work out this value, taking of log of this separate value and this separate value and subtract this, you will get the answer. See, I hope you may get this answer. Just I will repeat here. So 4 into 99 you will get, that is 396. Then simplification of this value will get 20.468 into 10 power minus 23, because in denominator 10 power 23, that's in becomes numerator, you will get 10 power minus 23. Then the A cube is what here? So after simplification of this method, you will get 19.347 into 10 power minus 23. So conversion of the 10 power minus 23 to 24, you have to put a dot 193.47. That's mean 19.3 become 193. So 193.47 into 10 power minus 24. So A is equal to what? Cube root of 193.47 into 10 power minus 8 centimeter. That is centimeter converse. That then A into the value after simplification you will get, that is 5.785 into 10 power minus 8 centimeter. Conversion of this unit into picometer. So 10 power 10 picometer. So A is equal to 578.5 picometer. Or alternatively you can use this method also. X, suppose if I have that A is X means cube root of 193.47. So X is equal to 193.47 to the whole power 1 by 3. Taking of log, so log X is equal to 1 by 3 into log of 193.47. So log of 193.47 value is 2.2867. So 1 by 3 into 2.2867, you will get, multiplying this value, you will get 0.7622. Here log X, this is log X. So that conversion of that log X to X mean you have to take anti-log. So anti-log of this value, you will get 5.785. So the values are same. You can use either this method or this method. See, next look at this numerical. An element with the density 10 gram per centimeter cube forms a cubic cell with the edge length of 3 into 10 power minus 8 centimeter. Then what is the nature of the cubic unit cell if the atomic mass of the element is 81 gram per mole? So here again write the formula, density formula. D is equal to what? D is equal Z into M divided by A cube into Na. So this is the formula, you know that. Now here we want to find out what is the nature of the cubic cell. That means Z we want to find out. That is the nature of the cubic cell. So here the density, element with the density is given here. So D is equal to what? 10 gram per centimeter cube. Then M, molecular mass of the, that is the atomic mass of the element also given, that is M is equal 81 gram per mole. Then A cube is what here? The edge length. A is what? Edge length. So A cube is, that is not A cube, A. So A cube is, sorry, A is 3 into 10 power minus 8 centimeter. Then finally Avogadro value, you know that the Avogadro value is Na, that is 6.023 or 022 into 10 power 23. So 10 power 23 mole, that is the unit edge length, sorry, Na value. Then apply this value, and before that you have to rearrange the formula. We want to find out the Z. This rearranged formula carries half mark. Usually the rearranged formula you have to write. So Z means you have to write, that is A cube into Na into D divided by M. So this is the rearranged formula. So we want to find out this value. So Z value. Here the A cube, the A is what? 3 into 10 power minus 8 centimeters into cube, because of A cube. So that whole power cube. Into Na is 6.022 or 23, 10 power 23, and the D is 10 divided by the M is given, that is 81. Now simplify this, you will get, that means 3 into 10 power minus 8 power 3. So this means 3 power 3, then 10 power minus 24, then 6.022 into 10 power 23 into 10 divided by 81. Simplify this. I hope you may get this answer is 2. That means Z is 2. When the Z is 2 means the structure will be what? BCC unit cell, that is BCC structure. So this is the answer. You must mention the BCC structure. This is the very important thing, because the question is what? The element, what is the nature of the cubic unit cell? Suppose if you write up to this mean, you may lose half mark, because the question is like this. You carefully note down the question. What is the nature of cubic unit cell? Here the cubic unit cell is what? BCC structure. You have to write. This is the very important thing. You have to write that BCC unit structure. Look at this numerical, students. An element with density is 11.2 gram per centimeter cube forms an FCC lattice with edge length of 4 into 10 power minus 8 centimeter. Calculate the atomic mass of the element. Already we seen the finding of A, already we discussed. Then Z calculated. This type is finding of the molar mass of the element. So here first write it. The formula is what? D is equal to Z into M divided by A cube into Na. So this is the formula. Now look at this numerical and write the values of each and every compound. See, for example, the D density is given. So D is 11.2 gram per centimeter cube. Then forms an FCC lattice so that Z will become 4 definitely, because of FCC lattice. In that question is given for a number of atoms in the FCC unit cell is 4, that is why Z is 4. Okay. Then edge length of the unit cell, here the A is also given 4 into 10 power minus 8 centimeter. Then you know that the Avogadro number value is 6.023 into 10 power 23 mole inverse. So these are the values. So we have D value, we have Z value, we have A value, and we have the Avogadro value. So we want to find out the M value. That means atomic mass of the element. So rearrange the formula. M into what? That is D into A cube into Na divided by divided by Z. So this rearranged formula gets half mark. Now apply this value. So applying of this value, D is what? 11.2. Then A is 4 into 10 power minus 8 to the whole cube. Then because of A cube into 6.023 into 10 power 23 divided by Z. So Z is 4. Now simplify this, you will get that is 11.2 into 4 power 3 into 10 power minus 24 into 6.023 into 10 power 23 divided by 4. Simplify this. See, this is the answer. So 11.2 into 64 into 6.023 into 10 power minus 1, because of 10 power minus 24 and 10 power plus 23. So that you will get 10 power minus 1 divided by 4. So 4 into 64 you will get 16. After simplification you may get that is 1079.32 into 10 power minus 1. That conversion of the 10 power minus 1 in molar mass means that is 107.9 gram per mole. So this is the atomic mass of the element. See, look at this question. Examine the given defective crystal. So x plus y minus x plus y minus x plus, and the second pattern y minus x plus y minus x plus y minus x plus y minus x plus electron given here, then x plus y minus x plus y minus x plus y minus. So the question is, you have to answer the following question, that is, what type of the defect indicates in this system, that is the defective crystal. And the second question is, write the term used for electron, this is the electron occupied side, then give the example of the compound source in this type of defect. So usually in this type of pattern, the first question is the type of defect. So here in this type of defect, that is source non-stoichiometric defect. The first question answer is non-stoichiometric defect. Then the second question answer is write the term used for electron occupied side. So here the electron occupied side is what? Usually you know that F center. So the answer is F center. Then third is what? Give the example of compound shows this type of defect. You may well know that is the lithium chloride, usually this type of defect source. So lithium chloride on heating gives an vapors to form this type of defect. So this is example is the exact example is lithium chloride. So this is the answer, and you have to write like this. This is the key point. So just write the key point here. So what type of defect? Simply you can finish it, non-stoichiometric defect. Then write the term used for electron occupied site, just F center. Then give the example of the compound source, this type of effect, that is lithium chloride. So this is the key point. Look at this question, students. What is the type of the non-stoichiometric point defect is responsible for pink color of the lithium chloride? Usually the non-stoichiometric defects are classified two types. One is metal excess defect, another one is metal deficiency defect. Here in this compound, in this question, what type of non-stoichiometric point defect is responsible for the pink color of the lithium chloride? Because here the pink color, already you know that alkali halide, that is like alkali halide, sodium chloride, potassium chloride usually shows this type. This is also one of the alkali halide, that means lithium chloride. So when a crystals of that lithium usually heaters on the atmospheres of the sodium vapors, what happened? That they are deposited in the, that is the cations are deposited and the anions are usually diffuses on the surface. That is why this type of the lithium chloride shows the metal excess defect. So the answer is what? You have to write metal excess defect. Then the second question, what is the type of the stoichiometric defect shown by the NaCl? NaCl, you know that very well, that is the Schottky defect. That is given that example, Schottky defect, one of the examples is NaCl. Then the third question, the density of the substance in the vacancy defect. Usually, you know that stoichiometric defect, the stoichiometric defects having, that is metal excess defect, vacancy defect, that different types of defects are there. Here, the density of the substance in the vacancy defect is decreases. So density of the substance, you have to write the decreases in the density of the substance, because vacant space is created. That is why the density of the substance is decreases. Then the density of the substance does not change in the crystal, that is in Frenkel defect. In a Frenkel defect, the equal number of the cations and the anions missing. That's why the density of the substance does not changes. So that the answer is what? Density of the substance does not change in Frenkel defect. Then give the example of both Frenkel and Schottky defect in the ionic crystal. See, usually the AgBr, silver bromide source, that both Frenkel and Schottky defect in the ionic crystal. This is the common example for both Frenkel and Schottky defect. Okay. See, the next question is the efficiency of that is the packing efficiency calculation. In this question, I am going to tell you that packing efficiency calculation for the body centered cubic structure. See, you may see that body centered cubic structure, that is spheres along the body diagonals with the solid boundaries. You can see that here that figure, that is that diagrams clearly that shows atoms and center which will be touched with all other two atoms diagonally arranged. Then in a triangle EFD, look at this, the triangle EFD. So here B square is equal to A square plus A square, because of the triangle EFD. Here one is the part B, that another one is the A. So that B square is equal A square plus A square. That means B square is equal to 2A square. So B is what? Root 2A. Now in triangle AFD, look at the triangle AFD. So in the triangle AFD is C square, that is C. C is given there, that is C square is equal to A square plus B square. So C square is equal to A square. Already B value we know that. See, 2A square, that will become 3a square. So c square is equal to 3a square. This means c is equal to root 3a. Now the length of the body diagonal is c is equal to what? 4r. You have to count that number of r. That means the circle, the inner circles are given, that inner circle you have to, one circle contains 2r. That is totally here one circle is 2r, one is half, that is in f near, in a near, that is 1r. So that totally 4r. So r is the radius of sphere, that is the atom. So all the spheres along the diagonal to touch each other. That's why root 3a is equal to 4r. So that a is equal to what? It would be 4r divided by the root 3. So r will become root 3 by root 3a by 4. So in this type of the structure, the total number of atoms are, that is 2 in their volume. So that 2 into 4 by 3 pi r cube. So volume of the cube, a cube, will be equal to the what? 4 root 3, 4 divided by root 3 r into cube. That is whole power cube. R you can write it, a cube is equal to 4 by root 3 r power cube. So the packing efficiency calculation, here you have to write, that is the packing efficiency calculation formula is what means volume of occupied by the two spheres in the unit cell into 100 divided by the total volume of the unit cell. So packing efficiency is the percentage calculation. So that the volume of occupied two sphere in the unit cell is what? Already we know that 2 into 4 by 3 pi r cube into 100 is given there, divided by the total volume of the unit cell. So the total volume of the unit cell is 4 by root 3 into r cube. So after getting, you will get nearly 68%. So the packing efficiency calculation of the body centered cubic is 68%. Similarly, you can see that already I teach you, that is packing efficiency calculation in that lesson videos, HCP, CCP, that is body centered, face centered. Just I recall this thing. So just practices the packing efficiency calculation. Hi students, see all these things are covered, like the numericals, compound identification, that is formula identification, density based numericals, packing efficiency calculations. So the types of defects also we were seen. See, just prepare well your examination and do well your examination.